Okay, so in this video we're talking about the concept of a sampling distribution. So just briefly, a sampling distribution refers to the shape and properties of the distribution of a random variable that we're interested in, right? So to illustrate this idea, I put some real data on the board. A lot of times concrete examples make concepts like this that are kind of abstract sink in a little better. Hopefully at your university, your professor has used an applet of some sort, a computer applet, to help visualize this on the board. That works really well, and the new applets that are out today really make it sink in and make it more visual. However, this example is just to introduce the idea, and I think you'll get enough out of this to have the basic overview of what a sampling distribution is. Okay, so let's look at what I have. I have grades on exam 2 for STA 2122. That's a class in elementary statistics we teach here at FIU. And we have these scores here beneath that, right? These scores are actually the first 5 grades I pulled from my grade book from last semester. So we have a grade of 100 for the first student, a 94, a 61, an 89, 78, ... It keeps going, right? Let's say for argument's sake this class was 49 students. Then what I have here is I have a list of STA 2122 grades for classes of size 49, so 49 students in those courses, and I have the class averages for exam 2 for those classes. So these are the average grades obtained on exam 2 for different courses, and this is one class's exam 2 grades, a sample of those. So when we look at these grades, for example, if I took all of them and plotted them on a number line, so I had maybe thousands and thousands of exam 2 grades for my students from different classes, and I just plotted them all on a number line, we would get a shape, right? We would get a shape, and we would then maybe be able to, by graphing a histogram or something like that, we might be able to get an idea of what the distribution looks like. And let's say after we did that, we discover that the shape of that distribution turns out to be bell-shaped, right? In fact, it's very common for the shape of distributions of test grades to be bell-shaped. That happens a lot. And it's also pretty common for them to have averages of, say, something like a 76, something in the C's or middle C's, and a standard deviation, let's say, of like 12.3. So these numbers are made up, but I bet they're pretty close to the actual exam 2 averages. So from experience, looking at the mean and standard deviation for the sample mean and sample standard deviation for classes of 49, I typically see results something around this order. Now, we're going to imagine that the population average, if you can plot all of these values, is 76, and the standard deviation is 12.3. And this kind of gives us the property of this curve. In fact, let me redraw it. It's kind of unattractive there. Make it look a little better bell-shaped. But so the idea is that the curve might look, something like that. It's a bell-shaped curve centered at 76 on the number line, and its variation, or the spread in the data, is 12.3, right? So again, try to remember what these concepts measure. This is where that curve is centered on the number line, and this is kind of the variation or the spread in the data, how spread out the values are, what are the differences in the data, right? Now, the idea of a sampling distribution is to talk about that idea for a random variable, for example, such as x bar. Now, if you look at that number, 78.2, it was obtained from a class average for exam 2 for a class of 49, right? So we could call this, for example, our first x bar, right? And then this number would also be an average. It'd be maybe our second x bar, and this would be our third x bar, and this one would be our fourth x bar, and this one down here is our fifth x bar. So let's just say that for now. And then ... right? Keeps going. So let's say I had thousands of these averages, right? Say I taught enough so many years and had so many of these classes that I had literally thousands of averages for those students who took exam 2 in classes of size 49. And let's say I plotted those averages on a number line. And I did the same thing I did over here. I create a histogram and I get a feel for the shape of the curve. That's ultimately my question when I talk about sampling distributions. I want to know, what's the shape of the curve for x bar, for example, right? If that's the variable I'm interested in. So what's the shape of the curve for x bar? What are its properties? Where is it centered on the number line? What's the variation or standard deviation like for the curve, right? How spread out are these x bars? So let's talk about some things we have to know about x bar just to give some answers to these questions. It turns out that x bar, we're going to learn later from a theorem called the central limit theorem, it's going to turn out that x bar is going to have an approximately normal distribution, as long as the sample size is fairly large. So in this case, our sample size is 49. That's going to be large enough to assume that these x bars have an approximately normal distribution. So it's going to look kind of like a bell curve, like this one, right? Then, on top of that, we also know from that theorem, the central limit theorem, that the average value, so the average value of this variable x bar, is going to be actually the same as the average for x. And what's x? Well, these are average test grades, so x itself are individual test grades. In other words, these guys, right? So what we're saying is that the average of all these values would actually be the same as the average for the test scores, right? So if the average for all test scores on exam 2 turns out to be 76, then the average of all these class averages for exam 2 would also be 76. So I'm going to say that this curve also has 76 as its average. What that means is that if we put it together, we're going to say, hey, the shape of this curve, if I were to plot all these on a number line, the shape of the curve is bell-shaped, and it's in the same exact location on the number line as this curve. So you could kind of put them on top of one another on the number line. However, there's one difference, one major difference. We learn also from the central limit theorem that the standard deviation for x bar is not the same, however. It turns out that it's going to be far less varied. If you take the standard deviation that we had over here for test grades, the standard deviation for x bar will be related to that quantity. However, you're going to add this extra piece, which is that the standard deviation for x bar is the old standard deviation divided by the square root of n, where n is your sample size. So in this case, it would be divided by the square root of 49 or divided by 7. So you'd be saying essentially that these numbers have a seventh as much variation as these numbers do. And we can see that, right? In fact, we can't just see it, we expect it. When we take a class, we expect that. We expect that students individually, some will do very well, some will do relatively poorly, right? And we might have grades down here in the 20s or the 30s sometimes, and we'll have grades like hundreds and 94s, and then people that do 89 and 78. So we get a lot of variation when individual students are involved. But when you look at class averages, we don't see that same variation, do we? We see that these numbers are all pretty close to one another. And we expect that, right? We don't expect that one class who takes the same exam 2, given the same instruction by the same instructor, given the same type of exam, we don't expect that, one class is going to have a 78 average and another class has a 20 average. That's, something we don't expect to happen. So we're kind of intuitively aware that this process is true, that the standard deviation for averages is always far less than it is for individual scores. Now, what that means when we put it all together, though, if we wanted to know the sampling distribution of x bar, we know its shape, we know that it's bell-shaped, we know it's located in the same place as it was for the x values, and we know it's much less varied. So if I wanted to draw it now, I could say, well, it'd be in the same location on the number line, it'd be at 76 centered. However, it might be much more like this instead. Same location, same bell curve shape, but much less varied, so you see that it's much more narrow or skinny looking, right? And of course more peaked because more of the data is being stuffed towards that center. Okay, now, before I leave this topic, I just want to say that, a reminder, when you talk about a sampling distribution for a random variable, you're interested in those ideas, what is the shape of its curve, where is it located, where is the center of the curve, and how spread out are the items, right? So, for example, we don't have to talk just about x bar. We could be interested in, for example, the sample standard deviation. We might want to know, what are its properties? What kind of a curve do these values have? If I looked at all the sample standard deviations for all of these class averages, right? If I looked at that, I might say, what are the standard deviations going to look like? Will they be bell-shaped in nature? Where will their mean be? What would their standard deviation be? What would the variation be? Or the standard error for that item, right? So that's the question then, right? And just a last thing before we leave, this term, we can call it the standard deviation for x bar, but it's often called the standard error for x bar, okay? So they call it the standard error because x bar's role is to predict the mean, and of course, when it varies, in a way you could say it's making a mistake because its average is the population mean, right? And so if it's used to predict the population mean, when it varies from that center, it's varying from its target parameter, and in that case you might say that that variation represents an error, right? So, terminology aside, it's the same idea as a standard deviation for x bar. And again, sampling distributions don't just refer to sample means. You could be talking about standard deviations, you could be talking about medians, so on and so forth.